Okay, all right. So first of all, we need to know, so this is chapter number 5. So first of all, we need to know about what is the stack, right? We already know that what is the stack we have discussed earlier. We know that stack is last in, first out, right? Last in, first out means whenever we have an empty stack, so whenever we add elements after elements after element, so if we want to remove some of the element from this stack, we have to remove the last one,
Yes, sir. This
right?
is the
The last
last
one.
one.
So for the last one, so we are going to use the last one. Remember one thing, that this is last in, first out, which is the stack. We have another kind of stack which is called queue. That is actually opposite. That is first in, first out. If you think about the example, real life example, the stack example is whenever you put the plates on top of each other, right? And if you want to get one back from that stack of the plate, you actually get from the top, not from the bottom of the stack. And top of the plate is actually, you have put it right at the end, I mean that, or at the last. So that is the example of stack. If you think about the queue, which is the first in, first out, it is actually the queue in the bank, the queue in any queue where the whoever come first, who will go out first. That is, who get the service first. So these are the two different things. So make sure you don't confuse these two things, the stack and the queue. All right. So one more thing, whatever we watch here, this is actually a graphical representation of stack. Originally, our stack is not like that. This is a graphical representation. What does it mean? That it will help you to understand that what is a stack. But if you think about original memory location, the hardware is actually opposite of it. Why I'm saying this? Because generally, whenever you think about the stack, we can see that we put one number, we put another number on top of it. Actually, is growing upwards, right? Which is the graphical representation. But if you think about our original memory, let's consider this is our original memory, right? And in this memory we have this portion, which is the stack segment. I mean, that is the portion where we use for the stack. In this memory, each of the block is considered as 1 byte. So generally, stack starts from the higher position and grow towards the bottom of the memory. It's actually not like that. You start from here, you start putting the number here and go upwards. Not really. It's opposite. You start putting the number from here and going downwards. Downwards means lower part of the memory. That is, we consider higher part of the memory. Let's say this is 1, 2, 3, 4, 5, 6, like that. Okay, so the higher part of the memory, we start our stack operation from the higher part of the memory and we are going downwards. That's why I have said that this is just a graphical representation, because here we are thinking about a real life scenario, that we put something on top of it, then top of it, and then on top of that. So the stack is going upwards, right? But in the memory, whenever you use the memory for and by using the Pentium processor, you actually opposite. It's actually starting from the higher position of the memory and going down towards the lower part of the memory. Okay, by the way, we already know that this is the insertion. We know that this arrow marks represents the last inserted number. That is the pointer. Always this pointer is indicating the last inserted or added number every time when we are using, or when we are doing the addition in the stack. Same way, whenever we have to delete some of the number from the stack, you can see that the pointer is actually pointing out the last number. For example, this was the last number, so after delete this number, your last number will be this. So after delete this number, your number will be that one, like that.
Is it fast in, fast out?
Yeah,
So,
no,
this is the last in,
last in,
fast.
first out. Yes, because it was, because 1000 come first, right?
Yes, sir.
1000 come first, so you cannot delete 1000 first. You have to delete 100 1003 first, but 1003 come at the end, right?
Yes, sir.
That's why it is last in first out, and we know that we have to delete this one first. That's why the arrow mark is here. This is the pointer, so you have to delete this one and then this one and then the other one. Okay, so
Sir, I
yeah,
get this the previous one.
previous one, this one,
No,
this
sir.
one,
Yes, sir.
this one.
Yes, sir.
This is also the same. This is also the same. We are going to discuss that how we are going to store a number, because this is these two, 2 1 and AB is actually a hexadecimal number, which is this one. It is also the same, but it depends on how you're going to save the data, because you know that Pentium processor is using the little endian byte ordering. I'll come to that. Please wait. All right, please wait. We'll come to that step by step. It is better that we go step by step rather than we jump somewhere else. So that is our stack operation. So let us see that now how the Pentium processor is actually implementing this stack, right? So if you're using Pentium processor and if you want to implement this stack operation, we know that stack operation means push or pop, add or delete. Okay, so that is our implementation, or the operations or the instruction of the stack, push and pop. So whenever you try to implement this stack in by using the Pentium processor, right? Then we need two extra information. We need two extra space, not information. We need two extra space. One is the SS, you can see that. Another one is the ESP. If you remember, SS is the one of the segment in the 6 segment register, stack segment. All right, that is the third one, stack segment. And if you also remember, we have a pointer register as well, 32-bit. It is the extended stack pointer, right? Pointer register. We have two types of pointer register. This is a stack pointer. So it is extended ES pointer. That means it's 32 bits, and this is 16 bits. So we need these two extra register to implement the stack in the Pentium processor. Let us see how. In SS register, we are going to store the basic or the first memory address of the stack segment. For example, let's consider this is, as I said, this is our main memory. In our main memory, we have a very specific place which is for the stack operation also only. So let us consider that this is the area for our stack operation. Okay, and this is the starting byte. So SS register is actually stores the value of this initial segment of this entire stack segment. That means it saves the initial memory address of the stack in the memory. All right, so that is the uses of SS register. We have another register which is called the ESP, extended stack pointer. So this register is actually stored the offset value. The offset value is the difference between SS and the TOS. We know that TOS is the top of the stack. TOS means top of the stack. That means the highest position of the stack. Generally, the top of the stack refers to the last inserted number. That is always top of the stacks is actually pointed out to the last inserted number. So top of the stack is pointed out the last inserted number. This is actually an empty stack, that's why we don't have any number. We will discuss later that what is the problem. There is a problem here in empty stack. So ESP storing the offset value. Let us consider in this case, let's assume that we have 256 bytes is allocated for the stack operation. So if you imagine that this is an empty stack, if the SS store the initial value and we have 256 the offset value, that means this difference is actually 256. The top of the stack and the basement of the stack, we have 256 because we have 256 bytes of space in the main memory, let's assume. Okay, that's why ESP is actually 256. That's why we say that we need two extra register to save these two information. One is the base address of our stack, another one is the offset value of the stack, right? Let us see that how we can insert or delete the stack. First of all, we need to consider about two situations. We need to consider about two situations. Oh, by the way, one more thing I forget to add, that we can use either as a word or double word. We cannot use as a byte, single byte. That is the characteristics of Pentium implementation. So I forget this one, that only word, that means a 16 byte, that means 2 bytes, 16 bit, or a double word, that means 4 bytes, that means 32 bits, are saved on the stack, never a single byte. That means it is not possible for Pentium processor to store a single byte of the data in the stack. Either it can be 2 bytes or 4 bytes, either a 16 bit or 32 bits. Okay, keep in mind. So we have two situations here in the stack. One situation is happened in the initial position where we don't have any number or any digits or anything in the stack. That means it is an empty stack. So whenever you first initialize the stack, it will be empty like this. That means the SS will point it out to the base address of the stack. ESP will contain the offset value, and the TOS, top of the stack, will show the top position of the stack. There is a problem. Not a problem, there is an issue. The issue is, if you look closely with the TOS and if you look closely to the SS, although it's a graphical representation, but still there is a meaning. The meaning of this is the pointing out the SS is actually not really the absolutely the base address of the stack. It's actually a little bit higher position of the base address. That's why whenever you add these two things, like the offset value and the SS value, then our TOS will go slightly after or slightly beyond the designated area of our stack. You can see that TOS is slightly beyond the position, because after that we don't have any stack operation. Do you understand? The SS pointing out little bit higher position than the absolute base address of the stack. So whenever you add these two numbers, because if you add these two numbers, then you can have the TOS position. So whenever you add these two numbers, because this is an empty stack, we don't have anything and we have entire value which is 256, then whenever we added these two numbers, the position of the TOS will go slightly beyond the area of the designated area of the stack. It is not an error, it is a situation, or is an issue. The name of this issue is called stack underflow. Stack underflow. If you want to read out this one, it says that when the stack is initialized, of course, TOS, top of the stack, points to the byte just outside the reserved stack area. It is an error, although this has said an error, it's actually not an error, it's an issue, to read from an empty stack. Okay, if you want to read something, or if you want to delete something from an empty stack, then it's an error. All right, so, and it is called, and it is caused, this error, by these issues, which is called stack underflow. That means whenever you try to read something, whenever you try to delete something from this empty stack, it will give you an error. And the reason of that error is stack underflow, because the stack is empty. All right, so this is an empty stack. That is one situation. Another situation we have, which is whenever you fulfill all the places, that means you have fulfilled the 256 bytes in the stack. Whenever you fulfill all these places or bytes, that means your TOS will come down and meet in the same place as SS, right? Whenever you are adding more, and then TOS is coming down, and in some point, let's say for example, this is our empty stack. We have added 2 bytes. Now look at the value of ESP. It is now 254. Previously it was 256. That means 2 less because we have added 2 bytes. Let's assume we add another 4 bytes here. Right? Now the TOS is here. Look at the value of ESP. Now it's 250 because we have added 4 bytes, 4 more bytes. So the EPS, the value of ESP is actually decreasing. So in some point, the value of TOS and the value of SS will be in the same point, right? What do you think when it will be the same?
When all the bytes are full.
Yes, when all the positions are actually filled up. That means when the stack is full, then the value of ESP will be 0 and the TOS and the SS will be in the same position. That means our stack is full. So when our stack is full, and if you want to add any more data in the stack, then it will give you another issue or another error, which is called stack overflow. Stack overflow. That means the stack full condition, right, is indicated by the 0 offset value. That means ESP will be 0. That means offset value is 0. If we try to insert a data item into a full stack, stack overflow occurs. So this one is the stack underflow when we try to read from the empty stack, and here it is the overflow when we are trying to insert a value into the full stack. Underflow and overflow, very simple. But the issue is both of them is actually can be handled. The overflow and underflow is actually a programming error because you can handle it by I mean by the programmer, because it's a programming error. You cannot read anything from the empty stack. You cannot add anything in the full stack. So it's a programming error. So we have to think about it. We have to consider it. Right, so that is the two situation, underflow and overflow. Fine, and that's how we can use all these three things, TOS, ESP, and SS. Fine. Now the question is how we are going to add. Let us see how we're going to add an empty stack, or how or what happened whenever we add some data in a stack. Let us consider we are going to add this number, as we have asked previously. We are going to add this number. Remember, H means hexadecimal number. So we are going to add this number, let's say for example, which is 21AB. We are going to add 21AB hexadecimal number into this empty stack. Now the question is, we are using Pentium processor, and we know that Pentium processor is actually using the little ending byte order. Remember? Whenever
Yes.
you try to store any number into the memory, the Pentium processor using little endian byte ordering. What does it mean? That means that you have to store the AB into the lower part of the memory. That means first, and then you go to the other one. That means, let's say for example, you have 2 bytes of space. First byte of the space and the second byte of the space. So you are going to save AB into which position of the byte? First position of the byte, right? And then you're going to store 21, which is the most significant number. We are going to store it into the second position of the byte. That means least significant number will go to the lower part of the memory, and the most significant bit will go to the higher part of the memory, right? Same way we are also using here. Consider this one, 21AB. We are going to add this into the stack. See how we have done. We have done little ending byte ordering. That means 21 should be in the higher position of the memory location, and AB should be the lower position of the memory location. I told you previously that we have started our stack from the higher position and going down. That's why you have to add 21 first and then AB, because AB should be in the lower part of the memory and 21 should be the higher part of the memory comparatively. Please don't get confused that you have to add AB first and then 21. Not really. What happened? Let's consider. If you think that if you want to add AB here and 21 here, do you think that it could be a right one? Because if you write AB here, that means AB will be in the higher position of the memory, and 2 1 will be the lower position of the memory. So it is actually not correct according to the Pentium little endian byte ordering, right? Because the least significant bit should, like this one, least significant bit should be stored into the lower part of the memory, and the most significant bit needs to store into the higher part of the memory. That's why we have added this number in this way, because we are using the Pentium processor. Let me give you another example. I hope it will be much more clearer. Consider this number. Again, H means hexadecimal number. So this is a hexadecimal number. We have 7FBD329A. So obviously, if you think that we have 4, this is 4 byte, this is double word. So we know that either we can do a word or double word. So this is a double word, 4 bytes. So if you think about the 4 bytes, so in the first byte position, which one we should store? 9A, right? Second byte position, 32. Third byte position, BD. And the fourth byte position, 7F. That means the least significant bit is stored into the first byte space. That means lower part of the byte. 7F is stored into the fourth position of the byte. That means it is stored in the higher position of the memory, right? Similar way, if you think about our stack, because our TOS is now here, that means we are going to add from this place. Look how we have added 7F first. Think about this one, 7F first, because this is the most significant bit, then BD, then 32, then 9A, because 9A must be in the lower part of the memory, because 9A is the least significant number. 9A, it should be in the lower part of the memory. It should be in the lower part of the memory. That's why 9A here and 7F in the higher position of the memory. As we consider that this is the higher position of the memory, that is the lower position of the memory, and that's why we add this number, 4 bytes of number, which is double words, in this way. So let us see now how we are going to delete the number. Previously you have seen how we are going to add the number. Now we are going to see how we are going to delete the number. Let me just remind you one thing. Previously the value of ESP was 256. After inserting 2 bytes, it is now 254, and after inserting the 4 bytes, now it is 250. That means the value is decreasing and the TO is coming towards downwards. This is for the insertion. If you think about the deletion, let us see how we can delete it. Now we can see that TOS is in the last position, which is the 9A. Now we are going to delete the number. Alright, we want to delete the 4 bytes we have added. Right? So we have, let's say we have deleted, we have pop the number, like this coding. We have pop the number. Pop means delete the number. So they will delete all this number. Or after deleting all this number, you can see that TOS will change its position from here to here. Like, see the position of the TOS. Previously it was TOS before the deletion. After the deletion, the TOS position is here. And look at the value of ESP. Previously it was 250, now it is 254, because the gap is increasing. Alright, but the interesting thing is, if you can see closely, that after deleting, the numbers are still there, right? The numbers are still there. Do you know why? After deleting, you can see that still our number is here. That means we're actually not deleting the number itself. We're changing the position of TOS and we're changing the value of ESP. That's why the pointer is right now here. Okay, so let's consider that, or let's assume that after deleting this number, we are going to add another number. Let's say, for example, this one. It is another hexadecimal number, 2 bytes of the data. So after adding 2 bytes of the data, this is the position. Look, 5, 6, 8, 9. That means 8, 9 should go to the lower part of the memory, and 5, 6 go to the higher part of the memory. That's why 7F is replacing by 5, 6, and BD is replaced by 8, 9. You can see that 3, 2, and 9A still remain same. although we are not considering that they are there. We are considering only the numbers have been added and before the TOS. We are not considering any number, very similar to our hard disk. Whenever you delete everything, it is actually not deleting the data. The data is still there in the hard disk, on your hard disk. You're just changing the location, you're changing or removing the address of those data. So if you have special device or if you have special software, you can retrieve the data after deleting. If you don't save so many, or if you don't do a lot of tasks after deleting, for example, after deleting, if you don't add these two numbers, you still can retrieve these four numbers. But what you can see that after deleting, we already added two numbers. That means you cannot now, after adding these numbers, now you cannot actually retrieve everything. Only can retrieve these two numbers because the other two numbers already replaced. That's why I said that whenever you delete some data, if you don't use your computer that much, if you don't use or save that much, you can retrieve your data. Same as here in the stack operation as well. Okay, so that is the insertion and the deletion of the stack. Last topic of this chapter, which is the uses of the stack. As I said earlier, if you want to use the stack by using the Pentium processor, we have three options, or we have three criteria, we have three parameters or three applications where we can use the stack. Although there are some others, but these are the three basic one. First one, where we use the stack as a temporary storage location. I mean, we use the stack, many of the times we use the stack to store the data temporarily, to do other tasks. Let's say, for example, you want to do other tasks. So you have to store some of the data into the stack for let's say for some times, for any specific time. After that, you have to take it back from the stack. In that case, you can use the stack. So that is one issue, temporary storage as a temporary storage. Another one is the transfer of the control. I hope you remember that in chapter number 2 we have discussed about the procedure calls. Although we have a procedure here, but we are not going to discuss right now. That's why I'm just giving you some idea that if you remember in that one, that the procedure call, that means, do you remember of the procedure call? That means you are doing some task, you have to jump to the other task and come back whenever you finish that task, right? You have to come back. So for coming back, you need to store some of the data. Let's say where actually you are going to come back. That means the return address. That means you are doing some task, you jump to the other task, finish the other task, and come back to the previous task. So that is the procedure. That is actually the procedure call, right? So this procedure call, to implement this procedure call, you have to store two information. If you remember, one is when you are going to finish that task, and after finishing the task, where you are coming back. So that is the return address. So for this purpose, we can use the stack. That is called transfer of control. And parameter passing also, we can also transfer some of the parameters by using the stack. All right, although they are saying that they are going to discuss in section number 5.7, but we are not going to discuss that one. So that's why I'm just giving you some idea, basic idea, that these three can be done, or these applications can be used, our stack operation. You remember the three things: temporary storage of the data, transfer of the control, and the parameter passing. Fine.